Good afternoon, all of you. Now, with respect to or in continuation with yesterday's lecture, that is overview of advanced machine process. Today, we'll go through the working principle of electrically energy based process. Okay, so let us start with the this EDM. Okay, yesterday we have seen that water jet machining, abrasive jet machining, abrasive water jet machining, and at last we have seen ultrasonic machining. Today we'll start with this electric discharge machining. Okay, in short, it is called EDM, and this process is belongs to the thermoelectric energy based non-conventional machining process. Okay, as per our syllabus, this is belongs to the electrically energy based process. Unit number 3. Okay, now as we are taking overview, so let us start with the its history part and the working principle. Okay, so this is another process. It is called electric discharge machining. Now let us see how it evolved or how it is developed. Okay, so the history part is that there were two brothers. Okay, actually there were two brothers named as Lazarenko brothers. Okay, here I have written that name. You can see at bottom. Lazarenko brothers were there in the older USSR. Okay, and one day what happened? They found that male and female parts of their switches. Okay, and they were having the dark matter deposited on their surface. So you can see that two switches also here. Okay, at bottom, whatever I have shown the two switches, no. So that brother found these two switches. So one is the male part, and the second is the female part, and both are that surface of that both part or pieces, it is deposited by the dark material. Okay, or I can call dark spots were there on that top surface of both pieces. Now whatever the some material had been removed from that male as well as the female parts, no. So by removing that material, they found that or that both brother firstly started thinking how to make use of this destructive phenomena. Now, how we can call it destructive phenomena? Because whatever the two switches are there, no. So on that surface, they found the dark spot. Okay. So that destructive phenomena. Okay. On that destructive phenomena, they have started thinking, and then they kept trying for years together and for developing many machines. Okay. To get the solution of that disturbed phenomena. A solution is what to for that disturbed phenomena want to convert into the constructive purpose. Okay, because now we know that simply by looking to that two switches, we can say that due to the sparking, some dark spot may happen on that two uh, part, female and male part. But at the time of that old era, they were unknown about this phenomena. Okay, so they have started thinking, and they want to convert this destructive phenomena to constructive purposes, and they have gone for the number of experiments, and after a long time, they were able to develop a machine which they named as a electro spark machining machine. Okay, electro spark machining machine. Okay, and they were able to develop that machine, and after that they have given the electric discharge machining. Okay, firstly they have given the name electro spark machining machine, and then after that they have given the name electric discharge machining, which is today we are calling as a EDM. Okay, and after developing they patented it, and they then whatever the we can call evolution of this machine, so that named on these two brothers. Okay, Now, the main, this is the history part. The normally the question arises that what is the working principle behind this process? Okay, what is the working principle behind this process? Now, if you see the diagram now, so there you will get that there is a dielectric fluid is there, okay, and that dielectric fluid flows between the your tool, okay. Now whatever the kerosene and water I have shown now, that is a dielectric fluid, okay, and they are flowing in between your tool and the workpiece. As we know that in advanced machining process or non-conventional machining, there is no physical contact between your tool and workpiece. So there is always some gap, and that gap is called inter-electrode gap, IEG, which is I have shown in this figure also. You can see, okay, and the kerosene and water, whatever flowing in between that tool and workpiece, no. So that IEG gap in between, in that gap, kerosene or water will flow. So dielectric flows between the tool. Now here tool will act as a cathode and workpiece will act as anode. Okay, because this is electric discharge machining. Okay. Now, as anode and cathode, as we know that both are electrodes. Okay, that means your tool and the workpiece, and they are connected to pulse power supply. That is pulse the DC power supply. You can see here. Okay, positive terminal of our DC supply, it is connected to the your workpiece, and negative terminal of your pulse the DC supply, it is connected to the your tool. Okay, and due to that, tool will act as cathode, workpiece will act as a anode. Okay, simply. And once potential gradient between the two electrode is more than, or I can call equal. Okay, I repeat, when potential gradient between two electrodes is more than or equal to the breakdown voltage of the dielectric, then the sparking will take place between that two electrodes. And this phenomena actually evolved by that two brothers. Okay, evolved by that two brothers, Lazarенko brothers. Okay, and due to that sparking, material removal happen. So that point or that conclusion they have made, that two brothers have made. Okay, so the basic principle behind this electric discharge machining is the sparking. Due to sparking only, material will be removed from the workpiece. Okay, now you may think that as tool as well as your workpiece both are electrode, okay, then so material may remove from the tool, that from tool surface, so that is 100% accurate. But whatever the material is going to remove from the your workpiece, so that quantity and whatever the material removed from the tool, so that whatever material removed from tool, that is minor as compared to your workpiece material removed. Okay, so sparking will take place due to, or when that sparking will take place, when potential gradient in between whatever the potential gradient supplied in between tool and workpiece, if it is equal or more than the breakdown voltage of the your dielectric, no, then and then only sparking will take place between the two electrodes, okay. And because of that spark, the material is removed from the tool as well as from the workpiece. And finally, whatever the shape of the cavity from on the workpiece is always inverse replica to the shape of the tool. Okay, whatever, simple, in simple word I can say, whatever shape or whatever cavity you want to produce in the workpiece, no, same cavity firstly you have to give to your tool. Okay, वर्कपीस मध्ये आपला जो शेप पाहिजे, ओके, इट मे बी असं खड्डा असू द्या किंवा ड्रिल असू द्या किंवा होल असू द्या, सेम तसा शेप पहिल्यांदा तुम्हाला टूल वर दिला पाहिजे. ओके, आणि स्पार्किंग जसं जसं होऊन जाईल तसा तसा ते वर्कपीस मटेरियल रिमूव्ह होत आहे, आणि जसा वरचा शेप आहे टूलचा तसा खाली तो निर्माण होऊन जाईल. दॅट सिम्पल वर्ड. ओके, लेट मी टेक, सम स्टुडंट्स आर वेटिंग. Okay, once again I repeat, here tool and your workpiece are not in physical contact. There is always some gap, and that gap is called inter-electrode gap, IEG. and in between that interrelator gap we have to flow directive fluid. Okay, now here question arises how to maintain gap, for what workpiece, which dielectric fluid should use. So all these things we are going to learn in chapter number 3. Here we are just taking the overview. Okay, just we are taking the knowledge of working principle. Okay, whatever I have shown that servo control, no. So the servo control is required because now every time that IEG gap is there, no interlude gap, that we have to maintain constant. Okay, so to maintain the constant IEG, we need to automatic process or system. So that is called servo control. Okay, so in detail we are going to see that time. Okay, got it. Now, as I have mentioned that the shape of the cavity from the on your workpiece, no, it is always inverse replica to the shape of the tool. Okay, now note that here what are the material is removed from your tool as well as from the workpiece. So that time the material removed from the workpiece or from the tool is always very less, okay, as compared to your workpiece. But as we know that we want to remove the metal from only workpiece, okay, which should not be got it. Now here what are the movement of tool I have show here, no. So to maintain that movement we require that servo control system. Okay, that is a part of the our EDM system or setup. Okay, that will say at the time of that point. Okay, so I think you understood that the working principle of EDM. Okay, if you have any problem you can ask. Now here itself I will clear that this electric discharge machine process is useful only for electrical conductive material only. Okay, your workpiece should be electrical conductive. Okay, now let us move for I will give 2 minutes to draw this diagram. So please draw the diagram. Yesterday I have not given the time, but from today onwards I will give the time to draw the diagram, because in our subject we have only diagram and then setup and where you have to explain. Okay, that much syllabus is there. We don't have any numerical part. So I will give the 2 minutes to draw this diagram. So all of you please draw this diagram. Okay. Now let us move for the next one. Now again, this laser beam machining. Again, this is a belongs to the category of thermoelectric energy based process, SGM process. Okay, but as per our syllabus, this laser beam machining, LBM, it is belongs to chapter number 5, that is thermal energy based process. Now let us discuss the its history and the working principle. Okay, now whatever the figure I have shown here, no, so here is an interesting activity, okay, which is we were performing at the time of our childhood also. Okay, so this is interesting activity of the children that they keep doing as a magic. Okay, so let's look at the figure, okay, at the slide only. So normally what children are doing, they take a lens, okay, which is I have shown here. Okay, they take a lens, then concentrate the sun rays on the workpiece of paper. Okay, sorry, they try to concentrate the sun rays using the lens, and that whatever the concentrated solar sun rays are there, no, they are striking on the piece of your paper. Okay, so see, sun is there, sun rays are coming through this lens. Okay, then concentrated sun rays are flowing on this or striking on this paper. Okay, now as we know that in the childhood, after some time, maybe 1 hour or 2 hours, this paper gets burned. Okay, so and that burning of the paper, we are calling it as a magic. Okay, at the time of our childhood. Okay, I think everybody has performed this experiment of this magic, I know. Okay, including me as well as you. So this, whatever the magic activity we were enjoying, no, actually this is not a magic. Okay, behind this, it is having the some technology. Okay, that is the burning of a piece of paper by concentrating sun rays. Okay, so children, they are enjoying this burning of the piece of paper, and they tell or call it as magic. Okay, so please, once again I repeat, please see the slide. Okay, now similar, whatever the sun rays are coming, no, from the sun, and by putting the lens in between our earth, or we can call paper, and the sun, we are putting lens. So due to that lens, we will get the concentrated sun rays, and they are striking that workpiece. So due to the heat energy of that, or we can call thermal energy of the sun rays, after some period of time, due to that heat energy on your workpiece, that workpiece will, or the piece of paper gets burned. Okay, that is a simple phenomena, or the behind the burning of the paper. So same kind of concept has been utilized in case of this laser beam machining. Okay, I repeat, similar kind of concept has been utilized in case of laser beam machining. Here you are concentrating. Okay, here I have diagram schema. So this is a laser beam machining diagram. Similar, okay, here you are concentrating the laser light at a very small spot on your workpiece. Okay, the workpiece that to be machined, or that to be, or to be given a particular shape and size. Okay, so here laser gun is there, like our sun. Then through that laser gun, we will get the laser beam. Okay, now then we are using the lens to concentrate that laser beam, and after concentrating that laser beam, we are concentrating on, or we are striking that laser beam on your workpiece. Okay, so here also the heat energy or the thermal energy of your laser beam, no, so due to that only, a removal of the material from the workpiece will happen. Okay, so removal of the material from the workpiece will happen due to only the heat energy content in the laser beam or thermal energy. Okay. Now, whatever the heat intensity of this laser beam is there, no, so that is very high. Okay, so you can so due to that high intensity, you can melt or you can melt and vaporize any material, okay, known to you. Okay, so you can use any material to melt that workpiece using this laser beam machine, because so whatever the laser beam we are getting from the laser gun, it's having the high intensity. Okay, and due to that high intensity, or we can call the that heat energy, melting and vaporization of the workpiece will happen, and due to that melting and vaporization, material will be removed from the your work. So that is the mechanism of material removed from your using this laser beam machine. Okay, and normally this laser beam machine technique is used for the material which is difficult to machine. Okay, I repeat, the material which is difficult to machine, for that purpose or machining of that material, we can use laser beam machining. Also, we can use this laser beam machining for high thermal conductivity material also. Okay. Now, there is certain problem with some material which have got high thermal conductivity and high reflectivity. No, so they can be machined by performance of they can be machined, but whatever the performance of this process is there, no, so normally it becomes a very low. Okay, the material having the thermal conductivity high and the material having a high reflectivity, so for that material the performance of this laser beam machining it gets low. Okay, now which are the materials having the high thermal conductivity and reflectivity? For example, here I have mentioned aluminum and copper. Okay, and whatever we get the machining efficiency, so it is normally very low. Okay, using this laser, less than 1% also. Sorry, more than 1% here I wrote. Okay, so this is the history part as well as the working principle. Please remember the point of the mechanism of material removal, like the melting and the vaporization is the mechanism of material removal in this laser beam machine. Okay, like yesterday I was telling that material removal mechanism of AGM is the erosion. Okay, so remember that action verb. Okay, now here also I will give 2 minutes to draw this diagram. Remember, this is important. You should know the working principle of all the processes. Here we are taking the work just the overview. Once again, the same process in detail. Okay, we are going to learn in the chapter number 5. Within 2 minutes, please draw the diagram. Okay, you may think about the how the laser gun will produce the laser beam. Okay, okay, which instrument is going to use. So in that we are going to use different system that we are going to learn afterwards. So I'm not going for that system, right? For the entire setup we are going to learn in the chapter number 5 about the laser beam machine. Here we have to consider only how metal is going to be. So the mechanism. So due to that only I have taken a simple diagram. Laser gun, okay, which will produce the laser beam, and lens will be there to concentrate that laser beam, and after that laser beam, we have to put our workpiece, okay, on which our laser beam is going to strike. Okay, and due to melting and evaporation, the metal removal will happen. How melting will happen? Due to heat energy. Okay, due to that only this process belongs to thermal energy based process. Every statement or the every that whatever the type we have made or category made, no, it having some logic. Now let us move for next process. Plasma arc combustion, PAM. Okay. So this is another process called plasma arc combustion, PAM. You can see in the diagram. Okay, this is a simple diagram I have taken regarding this plasma arc combustion or plasma arc cutting. Okay, normally it is called PAC, plasma arc cutting. Okay, so you can see in this diagram, you have the gas which is coming in. You have the gas. Here I have shown the direction also, gas. Okay, this is coming inside. Okay, and there is an electrode which is connected to the negative terminal. Okay, you can see this electrode, this pink color. It is connected to the negative terminal of DC supply, and whatever your workpiece is there, no, this, okay, this workpiece, it is connected to the positive terminal of your DC power supply. Okay, so this workpiece which is connected to the positive terminal, and in between this, here very high potential is applied across these two electrodes. Very high potential is applied in between these two electrodes. Now two electrode means the whatever the electrode which is connected to the negative terminal, and whatever the electrode which is connected to the positive terminal. Okay, so in between that, very high potential is applied across this electrodes, and under certain conditions, here arc will produce, okay, or arc will form. Okay, arc is formed, and whatever the gas is there also, that gas gets ionized. Okay, and due to that plasma is formed. Okay, whatever the gas is there, no, sorry, whatever the potential difference we have given in between this, no, so due to that, under certain condition, arc is formed, and whatever due to that arc, whatever the gas we have, no, so that gas gets ionized, and plasma is formed, and this plasma has very high heat intensity. Okay, and due to that very high intensity, it can cut any metal. Okay, so using that plasma we can cut any metal. So due to that only plasma arc cutting it is called. Okay, plasma arc cutting. Okay, I repeat, where we will apply the potential in between these two electrodes. So under certain situation or certain condition, arc will produce. Okay, and the whatever the gas is there, no, so that gas gets ionized, and due to that plasma will be formed, and due to that plasma we can cut any workpiece. Okay, so this is called plasma arc machining or plasma arc machining. Okay, so this is very interesting process. Okay, very useful process, but this process is especially used for rough machining or rough cutting only. Okay, it is not useful for finish machining purpose. Okay, if you want to cut any rough material or rough, sorry, hard material again for rough machining, you can use this process. Okay, and when we want to cut very high thick for very high thick material, okay, where electric arc cutting does not work, no. So at that place we can use the plasma arc for cutting those thick material also. Okay, so that is, if you want to cut thick material into pieces, that time we can go this arc cutting, plasma arc cutting. So this is about the plasma arc machining. Let's have the look at this figure. Now another process which is belongs to the thermal group, a thermal energy based process, that is electron beam machining, EBM. Okay, so there is another interesting process called EBM, electron beam machining. Okay, so uh, whenever we want to go for machining of micro holes, okay, or say filter of text, textile and food industry, no. So that time we can use this. Okay, so let us discuss the working principle. So here we have a lot of tungsten wire. You can see in this figure also. Here we have a lot of tungsten. Sorry, we have the hot tungsten wire filament. Okay, we have hot tungsten filament. You can see at the top. This is called hot tungsten filament, and it is used for emitting the electron. Electron. Okay. So this hot tungsten filament is used to emit the electrons. Okay. Now the whatever the electrons will be there, no, so it will have tremendous kinetic energy. Okay. Again, here you have that electron magnetic lens. Okay, electron magnetic lens. Okay, this blue color, electron magnetic lens, and beam control. This coil, beam control coils are used. Okay, so you have electron beam in which electron beam, here you can see, okay, electron beam will get from this hot tungsten filament. Here I have shown, and to concentrate that emission, electron emission, we have used electron gun. Sorry, electron gun. In that we have the filament. So electron beams will get here. So we have the beams in which electrons are moving at a very high velocity, which is close to the velocity of light. Okay, and such a high velocity electron, although they have not they have what negligible mass. Okay, and high, as I mentioned, it has high kinetic energy. Okay, and when these electrons hit the workpiece surface, that time they create very high temperature at that point where they hit the workpiece surface. Okay, when this electron beam will hit the surface of the workpiece, no, that time whatever the surface is there now, so there they create very high temperature. Okay, at that point only where they hit that workpiece, and when they hit the workpiece, no, after that high temperature, the temp whatever the temperature developed is, as we know that is so high, so due to that melting of the your workpiece material will start, and due to the melting continuously, the even evaporation will start in most of cases, and due to that melting and evaporation, material will be removed from the your workpiece. Okay, now here the condition is that in the whatever the we have the machining chamber, no, so it should have the vacuum. So due to that only you can see that I have shown the chamber, okay, and I have shown that this arrow high vacuum chamber, 10 minus of 5, sorry, 10 raised to minus 5 mm of each. So here for the electron machining, we need machining chamber, sorry, vacuumed or high vacuum chamber is required for the machining. Okay, so machining chamber should have vacuum. Now, so we'll take then another way. Okay, if air is there, no, in that chamber, so air means what? Low vacuum or no vacuum. Okay, then what will happen? The molecules of the air is there, no, so that will strike with the electron, and electrons will lose their energy due to that air. And if electrons will lose their energy, no, as a result, what will happen? You will not get the very fine cut on your workpiece or the component. Okay, that is law. So hence, mostly the vacuum is created in the machining chamber in this in this electron beam machining. Vacuum is created in the machining chamber, and that vacuum can be 10 to minus 5 millimeter of the your mercury. And however, there are certain versions of this electron beam machining machine also. Okay, where people are using air rather than vacuum also. But if you use air, that time efficiency is very low as compared to with vacuum. Okay, so this about the electron beam motion. Remember, whatever we get the electron beam now, it contains the very high kinetic energy, and when it will strike to the your workpiece, that time they will create the high temperature, and due to that high temperature means that heat energy. Okay, and due to that high temperature, melting and evaporation will start, and through that two action, or through that melting and evaporation, material from your workpiece will start to remove. Okay, so mechanism of material removal is the, or actual what is that, melting and evaporation. Okay, and temperature means what? It contains the heat energy. Okay. Now, last process belongs to the our thermoelectric process or thermal energy based process. That is ion beam machining process. Now, here I will tell about the focused ion beam machining. Okay, focused ion beam machining. Normally, in this focused ion beam machining, what are the splattering of or the knocking out of electron, of atom from the workpiece surface. Okay, and now I'm telling about the splattering of because in this focused ion we must splattering of will take place, and that splattering of means what? Knocking out of atoms from the workpiece surface by the kinetic momentum transfer from the whatever the incident ion is there, no, to the target atom. The target atom. Now this system of the ion beam machining, it is difficult to understand. Okay, we will simplify this. So knocking out of the atoms from the workpiece surface by the kinetic momentum transfer from the incident ion to the target atom. That is taking place here. And in whatever I have shown the figure, or in this figure, as you can see, the ion of the some gas is hitting the top surface of workpiece. The ion are hitting the top surface of the this. Okay, so whatever I have shown the dot, no, it is called your top surface of your workpiece. Okay, so the ions of some gas is hitting the your top surface of workpiece, and it displaces the atom from their particular point. Okay, so atom will displace. You can see here second diagram. Okay, so the energy with which the ion is hitting that top surface of the workpiece, no, is just sufficient, or the I can call ideal case is just sufficient to dissociate one atom from the your top surface of the your workpiece. So due to that, the here you can see the dissociation is happening. But normally, what are the energy of the ion is there now? It is much more than what you really just need to remove the one single atom. Okay, I repeat, normally the energy of the ion, whatever is there now, so it's much more than the what you really just need to remove the one single atom. And you can see in the above slide that you can see here, you can see in this both slide that iron has much larger energy than the bonding energy of two or more atom. Okay, bonding energy peksha energy content in the iron that is very high. So hence in place of one single atom, many atoms are removed from the top surface of your workpiece by a single atom. Okay, this second diagram you can see. Okay, so as a result of that, iron gets implanted below the top surface, and this can be seen in this above surface here also. Okay, and this is a situation which we really do not want in machining because surface gets damaged by that implantation. Okay, thus at sufficiently high energy, the what are the that there is a called a cascading event. Okay, so the when the ion penetrate more deeply into your solid, that time they eject several atoms or a molecule, and the bombarding that ion is done, so that bombarding ion becomes implanted deep within that material. Okay, so this whatever the mechanism is there, whatever the incidence of ions on the your top surface of workpiece, and due to the high energy of ion, okay, the displacement of the ion impartment will happen. It is called the ion beam machining. Like that, if you use the same phenomena for the machining, it is called the ion beam machining. Okay, so here high energy is required, and that high energy consists of ion having the whatever we are going to incident on your. Okay, so they actually the working principle of this ion beam machining is somewhat difficult. Now, only this electrochemical and chemical machining part is remaining. Okay, so that we will discuss after recess. Okay, now I will take the attendance for this lecture, and after 15 minutes at 4 o'clock we will start our the next lecture 4 to 5. Okay, at 4 o'clock we will have the another lecture. Now let me take the attendance.